Alice and Bob are trying to communicate with each other by sending bits one to the other. And suppose Alice sends exactly one bit, either a 0 or a 1, with equal probabilities. So suppose, let's say that Alice sends a 1, so the probability that Alice sends a 1 is equal to a half, and the probability that Alice sends a 0 is also equal to 1/2. Now if she sends a 0, then there's a 5% chance of an error occurring, resulting in Bob receiving a 1. So if Alice sends a 0, Bob receives a 1 with probability 0.05. So there's 5% chance of an error occurring. And if Alice sends a 1, then Bob gets a 0 with 10% chance, with probability 0.1. So this is the probability of an error occurring in case Alice sent a 1. Now, what we're asked to find is the following. We're given that Bob has received a 1, and we want to know, given this information, what is the probability that Alice actually sent a 1. So this is the probability that we want to compute. And again, we use Bayes' rule. We're going to use Bayes' rule and the law of total probability here. So in the numerator, we have the prior probability of Alice sending a 1 times the probability of the likelihood that Bob receives a 1, given that Alice has sent a 1. And in the denominator, we apply the law of total probability. So this is the probability of A sub 1 times probability of B sub 1 given A sub 1 plus the probability that Alice sent 0, but Bob received a 1, given that Alice had sent 0. So we have all these numbers, we can plug them in. The prior probability of Alice sending 1 bit is 0.5. Now, the probability of Bob actually correctly receiving receiving the 1 bit is 0.9. How do we know that it's 0.9? Well, because we said if Alice sends 1, then the probability that Bob gets a 0 is 0.1. So then the probability of Bob getting a 1 is 1 minus 0.1, which is 0.9. So in the denominator, we again get 0.5 times 0.9 plus the probability of Alice sending a 0 is again 0.5, and the probability of an error occurring if Alice has sent a 0 is 0.05. And we have our answer. So this is part A of the question. Now let's move on to part B. So part B says, to avoid these errors, to sort of increase the accuracy of the message, Alice duplicates her bit 3 times when she sends it over. So if Alice wants to send a 1, she will copy this one over 3 times and then send this over to Bob. Now, so this gets sent over to Bob. Now what it comes out to might be something like 1, 0, 1, because an error might occur. And the way Bob receives this message is he considers the majority. So the result is selected by majority. So what I mean by this is, since we have 2 1s and a 0, Bob says the initial message must have been a 1. If instead this came out to, let's say, 0, 1, 0, Bob would have assumed the initial message was a 0. And we're told that the initial likelihoods of Alice sending a 1 and a 0 are still the same, and the error rates are still the same. And we're asked that, given that Bob has received, so given that Bob has received 1, 1, 0, what is the probability that Ellis intended to convey a 1? So what is the probability that Ellis had sent a 1? So as before, we apply the law, the Bayes rule and the law of total probability. So we get the prior probability of Ellis sending a 1 times the probability that Bob receives message 110 given that Ellis has sent a 1. Now in the denominator we apply the law of total probability, so we copy over the numerator plus the probability that Ellis sent a 0 times the probability that Bob received the message 110 given that Ellis had sent a 0. So we know again the prior probability of Ellis sending a 1 is 0.5. Now the probability that Bob receives the message 110, well, if Ellis sends a 1, Bob will receive a 1 with so if Ellis sends a 1, that 1 gets tripled. So Ellis sends across the wire the message 111. Now the probability that Bob receives the first 1 correctly is 0.9, as we can see here. So this is the probability of Bob receiving an incorrect message, 0.1. So the correct message is 0.9. So the probability that Bob receives the first digit 1 correctly is 0.9. Then Bob needs to receive the second digit correctly. That's also 0.9, so 0.9 squared times. Now the third digit here, Bob needs to receive incorrectly, so an error needs to occur. And whenever Ellis sends a 1, the probability of an error is 0.1. So this is times 0.1 here. Now we can copy over that number in the denominator, 0.5 times 0.9 squared times 0.1 plus, now the probability of Ellis sending a 0 is again 0.5 times, now remember, again, Ellis is sending a 0, the 0 gets tripled and sent across the wire. So for Bob to receive 110, for the first 2 digits, an error needs to occur. And whenever Ellis sends a 0, the probability of an error occurring is 0.05. So 2 errors need to occur independently, so that's 0.05 squared times, and then the last digit, the 0, needs to come through correctly. And so if the probability of an error is 0.05, the probability of a digit coming through correctly is 0.95. And we have our answer.